So if I want to find the volume of a region, and I'm going to enclose it between some curves, I'm going to go about something besides the x-axis. So we're going to go about y equals 1, an axis parallel to the y-axis, and that'll make a different type of shape. And if I graph y equals x and y equals square root of x, the green is in the black there, we're going to end up with this region, all right? And this region has intersections of 0 and 1, which I show on the x-axis. And we're going to spin this, all right? We're going to spin this about the line y equals 1. Right? And everybody, I don't know if you can get a sensation, this banana is going to spin around this way today. All right? So we got to look at this.
Wait, how do you know which way you turn it around?
Whether you go over the top of it or over the bottom, we're going around y equals 1. We really can't go. I suppose you could look at it that way if you want. I don't care.
No, like, how do you know, though?
Because I said about y equals 1. That's how you know where the line is. Whether you go.
I saw that.
Okay, that's what the line is. Whether this little shape, either way you spin it, it's going to be the same. Whether you go.
Is it really?
Yeah.
Oh, okay.
Right, because if you spin it this way or this way, it's going to be that same shape. Doesn't matter. We're going to revolve it around. Now, everybody, if I leave that little butterfly, or whatever this shape is, a double banana, and I think of it this way, and I take my butter knife, and I cut into the board with that green line, and we spin it, what shape's going to be there? Huh? A washer. Yeah, it's going to be a washer. Guys, there's an outside circle and an inside circle. And if I try to do my best here to draw them, there's the outside, right? And there's the inside. If I kind of spin it. So that's my cross-sectional area, A of x, guys. And this is where we want to start every single time. We're not worried about the length of the radiuses at this point, right? We're trying to visualize the region. We graph the region and then try to figure out what shape, when you take your butter knife and cut through it, do we have. We have to memorize volume is equal to what? A to B of cross-sectional area dx. If I add up the areas in thinly sliced slivers, right, as I go across.
Mr. Anderson, I have a question.
Yes.
I don't mean to try and put a damper on your pronunciation or, words and stuff, but isn't it radii instead of radiuses?
I don't know.
It's radii.
I don't care. So that's a good. So it's radii. I want, and okay, I agree with you, the radii. But listen, you know why I call them radiuses? Because they're not the same function. And plural radii gives you the implication that these are the same function, and Ri and Ro are going to be completely different. All right? But you are right. I can live with that. But I don't want to send the idea that these two are at all related. Because the Ro and the Ri, and of course there's a dead spot on my board, are really different. And if I do this then, though, we should be able to see that, oh, hey, I can look at the green shape, throw on my Algebra 1 boots and write pi Ro squared minus pi Ri squared is that green cross-sectional area. All right? The problem is I cannot integrate Ro or Ri with respect to dx. So I have to change those into some sort of function. Now, invariably, this time of year, what I have students do is they just start guessing and, they'll just throw functions in. They hope and pray it's y equals x and y equals square root of x, and that x and square root of x become the radiuses, the radii. So the thing is anytime you go about something besides the x and y axis, it's always going to have the number involved. All right, it's always going to have the number involved. And Calista, I think you were getting this last week.
Oh my god, I totally know it.
All right, just hang on and let everybody else get there, because I know you know it, because you're seeing it now, aren't you?
That's the only thing I get in this class.
That's all right. We'll stick with the one thing and work forward. Everybody, if I blow this really up a lot, here's that y equals 1 line. See if I can do this to scale. I doubt it. There's the y equals x line. There's my x-axis. And there's my y equals square root of x. Everybody, if I do it with a, which line color I'm going to use? Blue. Everybody, do you see how the inside here, this is the RI, but this is also, and I'll call it y right now. I see that RI plus y has to be equal to 1. You guys agree? But what is y this time? Y is square root of x. And I want to solve for RI. So what is RI, Callista?
Okay. Shoot, you're putting me on the spot now. I lost my train of thought.
That's all right.
Okay. Ri equals 1 minus square root of x.
Yep. She's right on, guys. And it's the same story now for the other one. And you see that RO goes to the curve that's further away in this case.
So it's 1 minus x.
So it's 1 minus x. And we go down to our function now, or our integral, I should say, 0 to 1. I'm going to pull the pi out. We always pull pi out. Might as well do it now. RO is 1 minus x quantity squared minus 1 minus the square root of x quantity squared dx. And now we have done the integral with respect to find the volume. Now it's simply doing the math, squaring the binomials. What do we get when we square a binomial? We get a trinomial every time, guys. There's going to be 6 terms here before we do like terms. So I have pi, 0 to 1, 1 minus 2x plus x squared. Often I write below or above this binomial, so I 1 minus the square root of x is 1 minus 2 square roots of x plus x, but then I must distribute the negative. And I get that, and that's all dx. The dx is implied to all 6 terms, right? There are implied parentheses here. Very few math professors, including me, write them. But you need it for each integration. How many like terms are there? Well, the 1's canceled. That's nice, right? And the x squared is the highest order, so we'll put that first. Negative 2x minus 3x plus 2. And I'm going to write this as x to the half right away, everybody. It's easier. Everybody, every time it's 0 to 1, no plus c. When it's a definite integral of values, don't write plus c's. Alright, so I'm going to go down to a much larger view of this, because in the end now this is all just how fast can you do the work. This is section 410 if this is a struggle. Add 1, divide by the power, right? And everybody, when in doubt, take the derivative of x cubed over 3. Make sure that it is x squared. It is. Alright? Wow, that was all one thing. X cubed over 3 minus 3x squared over 2 plus 2. Add 1 to a half. I think it's 3 halves, right? And that's integrated from 0 to 1. I love problems with 1 because when I cube 1, it's still 1. I can pretty quickly do the math here. 1/3 minus 3 halves plus, plug in 1, take 2 divided by 3 halves, it's 4/3, minus 0, minus 0 plus 0 when I plug 0 in. And again, one thing to be very careful of here when you have something integrated to 0. If you have trig, guys, if you have sine or cosine, there can be values. You guys all agree? You got to be really careful when you have 0 as one of your limits of integration. Last thing, 1/3 plus 4/3 is 5/3. 5/3 minus 3 halves. This is maybe where I would actually use a calculator, but 10 minus 9. How about 1/6? And everybody, I can't stress enough, these are very long problems. Alright? And all the heavy lifting, the really hard stuff, happens right in here. Yeah, you would have to draw it. I don't know how you would know that's a washer. I don't know how you would do the cross-sectional area without a picture. And the problem here, eventually, is we're not always going to do circles. All right, we can define whatever we want as a cross-sectional area here. All right. The hardest part, though, often is doing the integration. All right. You get more mistakes down in this region, you know, like term mistakes, stuff like that. But getting this set up right here is super critical, and that's where the hardest, most difficult part of the calculus is.